All right, recently we have looked at vectors geometrically. We looked at a geometric description of vectors. Now we're going to look at the algebraic description. Geometric description was just really showing how vectors link together. We looked at the parallelogram idea to add vectors together and use the diagonals of parallelograms. And then also with subtracting vectors, you could use the other diagonal of the parallelograms. And we looked at their magnitudes and directions, all just geometrically represented, just as arrows, basically, or rays, with a defined length. And so now we're going to get into an algebraic representation. It's really going to help us to streamline some of those ideas. And so to develop this idea, I'm going to start by placing a vector on a set of axes, specifically so that the initial point is at the origin. Now, we've talked about this before, that vectors are defined by two things. One is their magnitude and the other is their direction, but not their position. So a vector's position is arbitrary. It can move around, it doesn't matter, it's the same vector. And so no matter where the vector is, it can always be moved to the origin, or so that the initial point is at the origin. And so everything I'm going to talk about with this vector can generalize to any vector no matter where it is, because a vector's position is not fixed. Okay? So I've got a vector, I call it vector v. It's at the origin of an xy coordinate system. Now, if I were to find the coordinates of the terminal point, I'm going to call those, I'm going to call that point AB, A comma B. Okay? So right there's a point A comma B. All right? Well, A comma B is a coordinate of that point, then I can construct a right triangle using those two values as the sides of the triangle. So on the bottom here we have A, that's our x coordinate of that point, and then the vertical side is B, right? That is the y coordinate of the point. All right, so that gives us some information about our right triangle. We also, because it's a right triangle, the right angle is down here on the right. The hypotenuse is the magnitude of v. Okay, so so the hypotenuse is magnitude of v in length. Okay, so now let's take a look at, we're going to define v algebraically. So here's the important part. So if the initial point is at the origin, the terminal point is at AB, then vector v is defined algebraically as A comma B with these pointy brackets around it. It looks like greater than and less than symbols. Okay, we use this notation to differentiate it from the point AB, which has parentheses around it. We use these pointy brackets, or arrows, I suppose, lots of different things people call them, to represent a vector. And this is the algebraically defined vector. This is how we would represent it. We use it coordinates, basically, of the terminal point. From there, I can determine what the magnitude is based upon what those a and b values are. We just use the Pythagorean theorem, right? The magnitude is a squared plus b squared, and then you take the square root. So the magnitude of v would then be the square root of a squared plus b squared. Again, that's simply the Pythagorean theorem at work. Okay? So now we have an expression based upon where that terminal point is for both the vector, the direction of the vector, and the magnitude of the vector. So we have both direction and magnitude represented here. Okay. Now, what's nice about this definition, is that if I were to try to add another vector to this, let's say I take a second vector, and I'm going to draw it in here draw it out here to the right a little bit. And I'm going to call this vector W. Okay. Then with vector W, it's going to have, another representation. We'll call it C comma D. Okay. Now C comma D is what you get if you take that vector and move it back to the origin. C comma D would be the endpoint or the terminal point, right? So if I were to take that same vector and run it parallel from the origin, let's see if I can make that look nice. Right about there. Then C comma D is the coordinates of the point, the terminal point here. All right, so that's C comma D as an ordered pair. All right, so the distance here, this is C. That distance, if you add it to A, think about how this works. You take the the x coordinate of the first vector, that's A. The x coordinate of the second vector is C. If you add those together, if I take the A value and then add the C value, I get this final endpoint, which is the sum of the two vectors. Okay? So the sum of the two vectors runs along the diagonal of that parallelogram. So that is V plus W. All right? So what we're getting is we're getting the coordinates to add up to get the sum. So the sum, which is, let me write out a few details of vector W here. So vector W is the vector C comma D, and the magnitude of W is, just like before, square root of C squared plus D squared. Then what we end up with the sum is V plus W will equal, again, you're just taking the A coordinate, or the X coordinate of both vectors and adding them together, and then the Y value, the Y coordinate of both vectors, and adding them together. So you get A plus C and B plus D to get the final sum vector, okay? And so as a general rule, if you add two vectors, A, B, and C, D together, you just add them by component. We call these components rather than coordinates. So coordinates are for points. The point AB would be coordinate A, coordinate B. The vector AB would be component A and component B. So here you add by components to get the sum. And then the magnitude of the sum is found by taking the square root of the sum of the squares. Just Pythagorean theorem. You take each of these quantities and square them. So you'd have A plus C squared and B plus D squared. Okay? And that would give you the magnitude of the sum. Now, of course, the difference is going to be the other vector, the other diagonal, I should say, the other diagonal on this parallelogram. Okay. What's interesting about all this is that, just like when we defined vectors geometrically, we could add vectors together using the parallelogram idea. You could also multiply by constants. You could say 2 times a vector doubles the length but keeps in the same direction, or 3 times a vector is triple the length, and so forth. Well, algebraically, the representation is, if you were to multiply a vector by a scalar, let's say 2 times the vector v, then you're doubling each of the coordinates. You double the x, you double the y, and that ends up doubling the entire thing. You're basically looking at similar triangles. You're blowing it up by the same proportion on each side. And so you end up with coordinates of 2a, comma 2b. To get double the magnitude, you have to double each of the components of that vector. right? And then the magnitude of that vector would then be the square root of, let's see, if you square each of those components, you end up with 4a squared plus 4b squared, right? Well, what's nice about that quantity is it has a common factor of 4 that you could pull out. So you could call that the square root of 4 times a squared plus b squared. And if you take the square root of each of those separately, which you can do with multiplication, you would end up with the square root of 4 times the square root of a squared plus b squared. The square root of 4 is simply 2. And the square root of a squared plus b squared is the original magnitude of v. Okay, so using the definition then, or using the Pythagorean theorem I should say, I can show that multiplying a vector by 2 and resulting in multiplying each component by 2 results then ultimately in doubling the magnitude of that vector. Okay, so the algebraic representation is consistent with the geometric representation that we talked about before. And we can do this for any constant. It doesn't have to be 2. I just like using the number 2 because everything works out well. But you can do that for any vector. So as a general rule, if I have any constant, I'll use the letter k, multiplied by a vector, then you multiply each of the components of that vector by that scalar k, or constant. Okay? When I use the word scalar, it means constant. They're interchangeable words. It just means a number, right? They're interchangeable terms there. Okay. And now there's some other interesting features. If I go back to this vector v, I can start to incorporate some trigonometry here. So let me, if you just kind of focus in on my original right triangle that I drew in, vector v, if I try to throw in some trigonometry here, I know that the sine of the angle here, if this angle, what do we usually call that angle? Theta? We'll call that angle theta. So theta being the direction of the vector, the sine of theta is equal to opposite over hypotenuse. That would be the b value over the magnitude of v, right? Because the magnitude is the hypotenuse. And so if I multiply both sides by that denominator, the magnitude of v, then I end up with an expression for the height, b, as the magnitude of v times the sine of theta. I can also do a similar construction with the cosine. We know that the cosine of theta is a over the magnitude of v, that's adjacent over hypotenuse. And so if I again multiply both sides by the magnitude of v, a is equal to the magnitude of v times the cosine of theta. Okay. We can also look at the tangent. We know that the tangent of an angle is the opposite over the adjacent side. So here, tangent of theta would be b over a. That may be useful later on, but for right now, we're really going to focus on the cosine and the sine formulas. Okay. In addition to those, we can really add and subtract any combination of vectors that we want. So here, the vectors v and w that I had before, if I wanted to find, 3v minus 8w, I could find that vector just by combining my expressions here, or my components. So I'd have 3v, which is 3a, 3b, minus 8w, which would be 8c and 8d, and And of course, if I put those together into a single vector, I would just have 3a minus 8c, comma 3b minus 8d. All right, so however whatever those a, b, c, d values are, you just combine them in this way, and you get your final vector. So sometimes we call this a linear combination of vectors, where you add or subtract just coefficients times the vectors together. Yeah. So a couple other things that are interesting. We're going to define something called a dot product. Okay. A dot product, so we talked about adding and subtracting and multiplying by a scalar, but now we can multiply two vectors together. So again, if I have vector v is a comma b, and vector w is c comma d, then we define the dot product as v dot w. It's a way of sort of multiplying two vectors together. And to do that, we're going to multiply corresponding components together and add those products. So it would be AC plus BD. Okay, we're going to multiply and add. Now, what you end up with is a scalar. You get just a number out, right? So if I'm multiplying two vectors together with a dot product, I'm going to end up with a scalar or a number as an output there. There is another type of product that you can do that gives you a vector as a result. It's called a cross product. It's not something that we cover in this class. It is something, if you get into vector calculus, or what we call calculus 3, you would really begin to explore that more, and then other classes later on after that. But for right now, the dot product is what we're going to use, because it's going to be quite valuable as we progress here